So in steady state processes, the derivative with respect to time is 0. So if I go back to my previous equation, if I have steady state case, what will happen? The derivative of the energy with respect to time will be 0, and I will end up with a simplified equation. So for a steady state process, first, the mass of my control volume is not changing, and the energy of my control volume is not changing. So from continuity equation, when we talk about continuity equation, is due to the conservation of mass. Okay, so from conservation of mass, I can say that sum of flow rates that are in is equal to the summation of mass flow rates that are out. And for the energy, if I replace into the first law of thermodynamics, then I can say that dE by dt is equal to 0. So I can say that the heat provided to the control volume plus summation of inlet fluxes is equal to the summation of the outlet fluxes plus the work done by the system. Because here I repeat that the convention we will use for the work, it is positive when done by the system and it's negative when done on the system. Okay, so in many cases we will consider together we have one inlet and one outlet, therefore the mass flow rate m dot is constant equal to m dot inlet equal to m dot outlet. By replacing in this case where we have one inlet one outlet, we have that the steady state equation is the heat provided to the control volume plus m dot times the energy of the coming flow rate, which is enthalpy at initial state plus v square over 2 plus gzi equals to m dot times this term plus the work done by the control volume. Okay. Now, we will do a lot of applications on these, okay, and we will start to do problems next time. But now we will continue with some definitions. Okay, so today basically we will cover some important definitions to be used in this chapter. And next time we can start doing application problems on everything we have done until now. Now, for the second law of thermodynamics. And this law is very important for you to understand after how, for example, refrigeration cycles work or how HVAC systems work, okay? So we have two classical statements of the second law of thermodynamics. We have Kelvin-Planck statement and Clausius statement, and both will give the same result at the end, okay? The first statement of Kelvin-Planck says that it is impossible to construct a device that will operate in a cycle and produce no effect other than the raising of a weight and the exchange of heat with a single reservoir. It might seem a little bit complicated, but it is a simple statement. It's saying that if I provide heat, so here, if you consider the following system, if you provide heat, you can never expect that all the heat you are given will be transferred completely into work. This is not possible. And this is why we will see this will limit the efficiency of our system. And we will try to do some engineering strategies to increase this efficiency. Because from experimental observation, it was seen that always, if I provide a certain heat, it will be divided into a certain work and a heat that is lost. I will always have a loss of heat to a temperature, to a reservoir at a lower temperature. So I can never completely transform my heat into work. This is why we don't have a thermal engine, a heat engine with an efficiency of 100%. It's impossible to reach an efficiency of 100%. Now, what do we do to increase the efficiency? To increase the efficiency of heat engine system, we try to benefit from the lost the heat we lose here. So here we are losing a certain amount of heat. We try to use it back, okay? If we use back the heat that we lost, we can save energy. So in this way, if we can have, for example, a heat exchanger, one idea is to have a heat exchanger, because once heat is lost, I can take it through a heat exchanger. It can heat, for example, a fluid, and this fluid will heat my system. So I can restore a certain amount of the energy lost. Okay? So this is the way Kelvin Planck stated the idea of the second law. Another possibility to state the second thermodynamic law is through the Clausius statement, saying that it is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a cooler body to a hotter body. So another statement is in this way. If I have, let's say, if I have two reservoirs, one at high temperature and one at low temperature, you know that naturally in a natural case, heat will flow from T cold to T hot, or from T hot to T cold.
Hot to cold.
Hot to cold. So this statement will say that it's impossible to have a flow from cold to hot without external intervention. We will see together in this course that it is possible to transfer heat from cold to hot, but we have a condition. What is the condition? Who has an idea?
A
What
heat
should I
pump.
do? Yes, I should provide work. This is what you call heat pump. Okay? So I should provide a certain work to my system that will allow it to transfer heat from cold to hot. And this is how your HVAC system works. Because in general, what you do is in summer, you want to cool your space, okay? While your space is at a lower temperature than outside, when you operate your system, it will reject heat from the inner space to the outer space, despite that the inner temperature is lower than the outer temperature. This can be possible only if you provide a certain work. Okay, while if you do not provide work, it's impossible to have heat flow from cold to hot temperatures. And this is what this statement is saying. So if you want, we can say that the main idea of the second law of thermodynamics is that we have what is called, here we will define what is called entropy. We have that if a system is left to its natural state, okay, it will increase its entropy. Okay, and we will see together what we mean by this. So from these observations done by these two researchers, we said that we can define another thermodynamic property that is entropy, which is a function of the state of the system. So the change in entropy of a system is determined by its initial and final state. In an ideal case, a process, okay, can be reversible. So if a process is reversible, what we mean by reversible, if I take a fluid from 1 to 2, if it can go back from 2 to 1, then this process is reversible. And in this case, the entropy will not change. While for an irreversible process, entropy always increases. Okay? And I will give you an example. For example, if you compress air and you leave it back, it will do expansion again. Okay? But if you do an expansion, can it compress alone?
No.
No. So this is an irreversible process. So when you have expansion, it cannot go back to the compressed state if I don't put a certain work on it. So we can say that when doing the expansion process, the entropy, which considers the state of energy of my system, will increase. Okay, it will increase, and I cannot go back to the previous state if I don't provide a certain energy. So from here, From the second law of thermodynamics, we can define a new property, the entropy, and it's defined as integral from the initial to the final state of the heat during a process over the temperature. Okay, now we will see together in this course that entropy will be useful to calculate energy exchange. Okay, I know that the second law of thermodynamics might seem a little bit complex, but all I want from you is just to understand that due to this law, we introduce a new variable, which is entropy, and together we will see in the course how to use the entropy. Okay. Any question until now? Okay. So now, what I will do, we talked about several thermodynamic properties, and we will see that in general, these properties are summarized in tables. So what we will do now, I will go a little bit over the thermodynamic tables, and we will learn how to use them in this course. We'll use them a lot, especially in power plants, okay, and steam power plants. So I will send you. I think that if you did the thermodynamic course, you might have worked with this book, and if not, I will post the link for the book so that you can access it, because you have all tables in this book. Okay, let me open the tables.
Doctor, somebody is in the waiting room.
Yes. Okay. Okay. Thank you. So just let me see where I put the tables, or let me open it again. Okay. So if you don't have this book, I will give you the link for it. Okay. At the end of this book, you can find all the tables we will use in the solution of problems. So here at the end, okay, you have two appendix A and B for all tables. I will go through these appendix, and in general, okay, when you have a problem, you can use any of. So you should be familiar with the tables to know which one to use in which case. Okay. So first, okay, so I will start from the first appendix. In appendix A, we will use more appendix B, okay? But in appendix A, you have properties for several fluids, okay? For example, here, sorry, I don't know why it's scrolling along, so just 1 second. Okay, so you can see here, for example, you have properties of solids at different, and liquids at different temperatures, okay? So for example, here you have this table for properties of solids at 25 degrees. They give you the density and the specific heat. Now, in this course, we will not deal a lot with solids, so we are mainly interested into liquids and into fluids. Okay. So for these tables, you might use, for example, table 5 for different ideal gases. So here, if you have a certain ideal gas and you have, but pay attention, you should stick to the condition. So for example, this table A5 is considering conditions only of 20 degrees 100 kilopascal. So if you have different conditions in your problem, you cannot use this table. But of course, if the information is not in these tables, I will give you extra information to be able to do the problem. So here you can see that for several gases, we can, depending if the state is 25 degrees 100 kilopascal, and we mean by this nearly atmospherical conditions, you can find the ideal gas value, which is R. You know that for an ideal gas, PV equal rho RT. Okay, so you can find in this table what is the value of R for different gases, what is the density, what is the specific heat, what is at constant pressure, and what is the specific heat at constant volume. Because we already have seen the importance of specific heat at constant pressure. If you remember, if we have exchange of heat at constant pressure, we can say that Q is equal, so Q dot of heat is equal to m dot times Cp times delta T if we have heat exchange at constant pressure. And if we have heat exchange, so this is for constant pressure. So in a problem, if they don't give you specific heat, you can go to these tables to search for the value of the specific heat. You have here the value for a specific heat at constant pressure and the value for specific heat at constant volume. Okay, and in case you have a gas, you can treat it in general as ideal gas. So you need to know what is R, because if you want to use the property of ideal gas, which is, for example, PV equals to rho RT, you need to know what is the value of R. So if you know R, you can use this equation to find properties. If I give you pressure and volume, you can find temperature, for example. Okay. So this is for the following table. And as you can see here, sometimes we know that the specific heat is a function of the temperature. In general, sometimes we can assume that the specific heat is not variable with temperature, but the condition is to have the interval of temperature variation should not be very high. So if you have large delta T, then it will be good to take into consideration variation of values for Cp and Tv. Okay. Now, if in a certain problem, okay, if they don't give you any information, or if you find that delta T is not very high, you can assume that Cv or Cp is constant. But if they provide you with some information, or if they give you a table, you should know how to use it. So here, for example, we illustrate how the specific heat is varying with temperature. Okay, so if I give you the formula of specific heat with temperature, you can compute how C is varying with the temperature. And instead of writing, for example, that Q is equal to m dot times mCp delta T, if Cp is not constant, what can I do?
Integrate.
I do integration. Okay, so I integrate m times Cp times dt, and Cp will be function of temperature. So as long as I have the specific heat as function of temperature, I can do the integration. Okay, so if I give you such a table, you should know how to use it. All you have to do is you have the temperature range you are working on, and this is your formula. As you can see, specific heat is function of temperature, and here they give you several coefficients, C0, C1, C2, C3. For different gases, they give you what are these coefficients. So, for example, if I have ammonia, let's say, and I want to find heat variation and temperature is, the range of temperature is very large, then I can find from this equation, I can replace C0 in this equation by for ammonia 1.6 C0, C1 1.4, C2 1, and C3 minus 0.7. So I replace this constant in this equation. I get the variation of Cp with temperature, and then I can replace into my integration. Now,
Miss, before you said that PV was rho RT, PV equals MRT, no?
yes, PV equals MRT. I mean by PV here, V is a specific volume. It's not big V when I write this, okay?
Specific volume بتصير PV equals RT.
Yes, you have that. Yes, John.
ما في density.
Yes. PV equals to MRT, okay? If you have the big volume, and if you write P times small v, it's rho RT, yes, true.
Okay. بس ليه rho?
Yeah, because if you divide, sorry. Yes. Rho, yes. Yeah. I see your point.
هذا قصدي.
Yes. Okay. If you do times, if you write just PV, the specific volume, so it means that you are dividing by, here you are dividing by the mass, so it's M, okay? Now, in general, if we define here, if you have an expression with rho, which is the following. You have that the mass is equal to rho times the volume, okay? So if you define this equation, if you divide by V this equation, then you will get rho RT, okay? So here in this equation, if you simplify V from the first equation, what do you get? This is what I mean. If you replace M by V, yes, you will simplify V and you will get rho RT. So if you replace M here by rho times V times RT, then if you simplify the volume from both sides, you will get that P equal to, so you can use either of these three equations for an ideal gas. Or you use pressure times volume equal MRT, or you use pressure equal rho RT, or you use P times specific volume equal to RT, okay? Anyway, these two, you can get one function of the other, so you can directly, because if you take rho to the other side, it will be P over rho equal RT, and rho is the specific volume. So these two are equivalent, okay? So now, here, for example, in this table, you have for atmospheric conditions, okay, you can use the following table to find the values of internal energy, enthalpy, and entropy for different temperatures, okay? So here, as long as you have the following conditions, that you are working at 0.1 megapascal, then you can use this table, okay, to find what are the values of internal energy U, enthalpy H, and entropy S for different temperatures. So sometimes we will see that in some problems, they can give you the temperature, and based on the temperature, you can get the value of U or H. And in open system, we will deal mainly with H, okay? While in closed system, we will deal with U. So now, for example, what if I have a temperature that is not in this table? So for example, if I want to find at 310, okay? If I want to find the properties at 310, I will do an interpolation, okay? For 310, in general, we assume linear variation and we do linear interpolation, okay? So here it's clear that it is in the middle. So I will say that U for 310 is equal to the average of these two values. Now, sometimes if it's little bit more complex, if I want at 308, for example, okay, how I do the interpolation, I will write the following. So for T equals to 300, for example, U is equal to 214.36, 214.36, okay? And I will take the values for 320. So for T equals to 320, the value of U is, so I cannot see it here. Let me clear everything. Okay, so here I will take the following values in this interval, okay, and I can do linear interpolation. What I mean by linear interpolation, I can consider that I have the values are on a straight line, okay? So U is varying in a linear way with temperature in this interval. So this is why I can write the following ratio. If I am interested in value at 308, which is somewhere in between, okay, at 308, I can write the following ratio, that 308 minus 300 over 320 minus 300, okay, is equal to, the whole idea is that for a linear variation, the slope is constant, okay? And how you calculate the slope here? If you want to calculate the slope, you do 228 minus 214 over 320 minus 300. The slope will remain the same, okay? Since your slope will remain the same, it will follow that this ratio will apply. So 308 minus 300 over 320 minus 300 is equal to the U value at 308, which should be calculated, minus the U value at 300 is 214.36 over the U value for 320 is 228.73 minus the U value for 300, which is 214.36. Okay, and this ratio, as I told you, is due to the linear variation. So you have the same slope. And from this equation, your only unknown will be U value at 308. So by linear interpolation, you can find any property at any temperature. Of course, the temperature should be in the range given here. Okay? Do you know, you are familiar with linear interpolation, I think. And
Yes.
if not, this is the technique you do. Okay? So by this way, you can, if you have the inlet temperature, you can compute the values of U and H. Now, for example, here, okay, you have also ideal gas properties for substances that we frequently encounter as O2 and N2, and so here you can see that if you have a certain gas, for example, it is N2 or O2, you have also tables for these gases, since they are these gases are widely used, okay. And sometimes you can directly therefore access this table to get the information about U and H for these gases. And here, for example, you have for other gases as nitrogen, you have N and N2. So here they will give you the variation of properties for these gases. Now we will move to steam tables, okay, and tables for different refrigerants. And so Appendix B, we will use it a lot, okay. Now we will see together that you have several states for water. You have water in the liquid state, you have water in the vapor state, you have water in the superheated state, okay? And depending on the state of your substance, you will have different tables, okay? So we have what is called saturated liquid, saturated vapor, and I will explain what do we mean by this, okay? So if you have water, so first, as you heat it, it is in the liquid state first, okay? We have already seen together that at the first step, as you heat it, it will undergo an increase in temperature. Then at a certain state, it will reach a change in phase, okay? So when you reach the evaporation temperature, you will have change of phase from liquid to vapor, okay? So during the change of phase, you maintain a certain constant temperature until reaching what we call the saturated vapor state. So this is, you have two saturated states. This is the saturated liquid state, and this is the saturated vapor state. And after this, you will have change of phase. So you have complete change of phase here from a liquid to a vapor, and then you have what we call the superheated state, okay? So for water, we mainly have three states. We have liquid, we have mixture, which we call saturated water, okay? So we have a percentage of liquid and a percentage of vapor. And finally, we have, once you have 100% vapor, it's the superheated state. So we have 100% vapor. And depending on the state, the thermodynamic properties will change, okay? So here we have 100% vapor, okay? Now, when they put for a table saturated water, so we are talking about this phase here, the properties of this phase. And in this phase, okay, you have that temperature and pressure are constant. They are not varying during this phase. And what is varying is just the percentage of liquid, and of course, therefore, the percentage of vapor, because you are moving from 100% liquid at this point to 100% vapor at this point. Now, this state, as we said, is the saturated liquid. So here, this, when we put this property here, saturated liquid, we talk about this point. So this will correspond to this column here. So you are giving the specific volume, for example, in this table, you are giving the specific volume for saturated liquid. So for this point, for a temperature of 0.01 and a pressure of 0.6113. We will see together that in the saturated state, you have always a certain couple of temperature pressure. So if this is the temperature, this will be the pressure of the saturated phase. And as you can see, if you increase the temperature, the pressure of the change of phase will increase also, okay? So now, these 2 points are very important, and they are the boundaries of the saturated state. You will see here that this value corresponds to the second point. So this is saturated vapor. So this point is saturated liquid. This point is saturated vapor. And we can define what is called VFG. And which is the difference between, so VFG by definition is VG minus VF, and we will see why we use it. We will use it a lot. This parameter will be used a lot. It's equal to the variation, the difference between VG and VF. No need if you want to provide it, because you can deduce it. Okay, you can deduce it since you can do the difference between the two. Why in general they give it directly, because sometimes for practical reasons you will use this ratio in general, this numbers. This is why they give it here. Okay, and you can have these properties. Okay, so F, property of saturated liquid, property of saturated vapor, and FG property for all the thermodynamics properties, specific volumes, specific internal energy. So here, for example, in this table, you have the values computed for the specific volume. Here you can find it, and for the internal energy. And we will see together that the remaining tables will give you also the enthalpy and the entropy. Okay. So here, for example, if we continue to scroll down in these tables, you will see that for saturated water, so they will also give you another table for the enthalpy and for the entropy. So it's the same values concerning F, saturated liquid, saturated vapor, and the FG. So HFG is the difference between AG and HF. And here you can, so it depends on the input you want. If you want internal energy, you will use the previous table. If you want the enthalpy, you will use this table. Okay, so here you have, as we said, for different temperatures, these tables cover a wide range of temperatures. This is why you have a lot of tables. Okay, so we are still in saturated tables, but look, sometimes you have two types of entry for this table. You can have the temperature or you can have the pressure. This is why for tables I provide you two tables, one if you have the pressure entry and one if you have the temperature entry. So if you know the pressure in your problem, you go to these tables where the pressure is the input, so they are organized by pressure value. And if you have the input in of temperature, you will go to the other tables, because for the other tables they will put them in order for temperature. Okay, so it depends on what are the given of the problem, you decide which table to use. So we will continue